Hello, my name is Anthony Francione, and welcome to the Whitebox Geospatial YouTube channel. Today, I'll be providing you a quick tutorial on how to filter a DEM using various tools within the WhiteboxTools Open Core. This is a common task for GIS and geomatic professionals when working with LiDAR or other types of data such as SRTM DEMs. DEMs can appear noisy, rough, or even contain speckle after being interpolated. This can be a result of multiple reasons, such as scanner error, miscalibration, or the underlying terrain is just inherently rough. This error or noise is not to be confused with surface roughness, which is actual topographic variation captured at fine scales such as those around 5 meters or finer. However, what surface roughness and noise have in common is that they both inhibit accurate topographic attribute extraction. It is common for GIS and geomatic professionals to apply certain low-pass filtering techniques to remove this error, surface roughness, and noise from DEMs. Such techniques include the mean or median filter. Although these techniques are effective at removing noise, they suffer from oversmoothing, in which important topographic features, such as drainage features, can be blurred as a result of their coarse smoothing nature. In today's video, I will show you some techniques for smoothing a DEM using WhiteboxTools and their associated impacts on topographic attribute extraction. Before we get started today, I just want to introduce the data set I'll be using. This is a 1 meter LiDAR DEM for a portion of J State Forest in Vermont, USA. This DEM has been captured under extreme forest cover, and the interpolated surface is extremely noisy and rough. However, you can see that there are many important topographic features, such as drainage features, that carry flow from this portion of J State Forest. It is important that the topographic expression of these features remains intact during the smoothing process. I interpolated this DEM using the natural neighbor or Simpson's method. If you're unfamiliar with how to create a DEM from LiDAR data, in a previous tutorial, I talked about how to do just that, so I'd recommend watching that video before. I've attached a link to that video in the description down below. So now that we're familiar with the DEM, I will introduce the 3 smoothing techniques that we'll be comparing today. All of these tools are located in the WhiteboxTools Open Core and can be downloaded from our website at whiteboxgeospatial.com. If you're unfamiliar with how to download and use WhiteboxTools, I've actually created a YouTube tutorial for that video as well, and I've attached the link to that description as well, so I would recommend checking that out too. The 3 smoothing techniques we'll be looking at today are the mean filter, the median filter, and the feature preserving smoothing filter. Let's take a look at each of these tools in the WhiteboxTools user manual. So I'm just going to navigate to our website. On our website, I'm going to access the user manual, which can be found on our Learning Resources page. Once on our Learning Resources page, going to the WhiteboxTools user manual, and then once in the manual, you're going to want to navigate to the tool. You can either do so by searching for it in the tool index, or if you know where it's located, you can go to that certain toolbox. The mean and median filter are located in the imaging processing toolbox in the filter toolbox. Once in that toolbox, you'll see the mean and median filter. The mean filter is a common smoothing technique applied to a raster image that takes the mean of the filter window size. The algorithm operates by calculating the average value in a moving window centered on each grid cell. Neighborhood size or filter size is specified in the X and Y dimensions. The mean filter is commonly applied to reduce noise in the image, but it can be quite harsh in respect to the output image. This tool has 4 outputs: the input file, the output file, the filter in the X direction, and the filter in the Y direction. The next tool is the median filter. The median filter is another low-pass filter that applies a local median calculation on the filter window size. Median filters can be used to emphasize the longer range variability in an image, effectively acting to smooth the image. This can be useful for reducing the noise in the image. This algorithm works by calculating the median value in a moving window centered on each grid cell. This technique is not as harsh as the mean filter, but is also less sensitive to short-scale noise, which is common in LiDAR and SRTM DEMs. This tool has 5 input parameters: the input file, the output file, the filter in the X direction, and the filter in the Y direction, and lastly, the number of significant digits. Let's take a look at the feature preserving smoothing tool next. This tool is located in the geomorphometric analysis toolbox. This tool is much more complex than the mean and median filter. This tool implements a modified denoising algorithm based on the Soon et al. 2007 mesh denoising algorithm. This tool is very effective at removing surface roughness from digital elevation models without significantly altering breaks and slopes. This algorithm works by first calculating the surface normal 3D vectors of each grid cell in a DEM. Next, smoothing the normal vector field using a filtering scheme that applies more weight to neighbors with lower angular differences in surface normal vectors. And lastly, it uses a smooth normal vector field to update the elevations in the input DEM. The user must specify 3 key parameters, including the filter size, the normal difference threshold, and the number of iterations. Lindsay et al. Found that the degree of smoothing was less impacted by the filter size than it was either the normal difference threshold or the number of iterations. So to increase the level of smoothing applied to DEM, consider increasing the normal difference threshold or the iterations parameter. Just going to show you a quick image comparing the actual, looking at the technique. So this is a portion of a DEM before a smoothing treatment, and this is a portion of the same DEM after treating it with the feature preserving smoothing tool. So you can see that much of this roughness and these lumps and bumps have actually been removed as a result of smoothing, and the salient topographic feature, in this case, which is a large drainage feature that extends through this portion of the DEM, has remained well intact as a result of smoothing. So now that we're familiar with the data set and the tools we'll be using today, let's go ahead and get started. First, open up a new terminal window and cd into the WhiteboxTools directory based on your environment. For myself, that's located in my Documents folder, in another folder called Anthony WBT Tutorial. And once in that folder, we're going to go to the WBT environment, which you can see here is our WBT environment. And here I have the Whitebox runner front end and the WhiteboxTools executable. So we're just going to go ahead and launch that front end using the command python3 wbrunner.py. So once the front end launches, we're going to go ahead and run the mean filter. So let's navigate to the image processing tools, specifically the filtering toolbox, and then look for the mean filter. So as you can see, the input files, we're just going to start populating them with the data. We're going to put the JState forest unfiltered DEM in as the input file. We're just going to call this test.tiff for now. The filter in the X direction will be 21, and the filter in the Y direction will be 21 as well. This is normally a bit larger of a filter size than I would use for this size of DEM, but this DEM is extremely rough as a result of being captured under forest cover and needs a more aggressive smoothing approach. I'm actually just going to add test_mean_21 FS, so we know it's the mean filter and it's been filtered with a filter size of 21. So now that we have all the information, I'm just going to go ahead and hit run. This tool is pretty efficient as a result of the integral image approach. If you want to read more about that, you can actually check out the tool itself, but this tool executes in 1.25 seconds. So now that the mean filter is completed, let's just make a quick hillshade of the output filter mean DEM. When comparing filtering techniques or other topographic attributes, it may be difficult to see the difference in the DEMs themselves, and thus it's always good to create a hillshade to give you a more accurate representation of the surface. The Hillshade tool is located in the geomorphometric analysis toolbox, which is the same toolbox as the feature preserving smoothing tool. And there we have the Hillshade tool. So let's just go ahead and start inputting the values. So we're going to put the mean filter, and we're going to call it the same thing. And we're just going to add _Hillshade. The azimuth and altitude parameters control the illumination source for the calculation of the Hillshade algorithm, but I'm just going to leave these values at the default as they are fine for this tutorial. So now that I have all that information inputted, I'm just going to go ahead and hit run. We will view the output of the Hillshade tool after when we're actually comparing the DEM, but now that the Hillshade is created for the mean filter, let's continue the same process with the median filter. So let's head back to the image processing tools, the filtering toolbox, and go to the median filter. And let's just once again put all those same parameters in. The unfiltered DEM, we're just going to call this test_median_21 fs.tiff. We're going to do the same size of filter window just for like a similar comparison. And I'm just going to bump the number of significant digits up just slightly, just to 3. And I'm going to hit run. This tool is also pretty efficient. It doesn't actually use an integral image approach, but it is a simple calculation, is a median calculation, but this tool will scale with filter size. Once again, now that that tool is created, we're going to create a hillshade for it as well. We're just going to input the median DEM. We're just going to call it the same thing, test underscore median underscore 21 underscore hillshade. And we're just going to leave these parameters as default, and we're going to run it. So now that the median filter is complete, and we've created a hillshade for it, let's actually go create the feature preserving smoothing output. So that tool is located in the geomorphometric analysis toolbox as well, feature preserving smoothing. So this tool has 7 input parameters. The input DEM will be the unfiltered JState forest DEM. The output file we'll just call test underscore FPS. And we're going to use 21 as well, so we'll just do that for now. The filter size, we're just going to keep constant with the other filter size, which we're going to use 21, just like the other tools. The normal difference threshold controls the maximum allowable deviation in normal vectors, meaning if the value is exceeded, the feature is a significant breaking slope, and thus we do not want to filter it. If it is less than the threshold, the feature is not a significant feature, and thus we can filter it. I'm just going to raise this value to 25 from the default of 15, just because this DEM is located in such a mountainous terrain. So I'm just going to bump that up to 25. The iteration parameter controls the elevation updating procedure, in which more iterations result in more smoothing. Once again, I'm just going to bump this value up a bit just because it's such a rough DEM. I'm going to bump it up from 3. I'm going to go to 5. Next, the maximum elevation change controls the maximum allowable change a cell is allowed to endure as a result of smoothing. This cell changes by more than half a meter. The original value will be used instead. This parameter is used to stop the creation of single cell pits as a result of smoothing. Once again, I'm just going to bump this value up a bit. I'm actually going to go to 1.0, so 1 meter. There are many lumps and bumps that have been interpolated on the bottom of the forest floor, and we kind of want to remove them. Lastly, the Z version factor, I'm just going to leave blank. So now that all the parameters are set, we are just going to go ahead and hit run. This tool will certainly take a bit longer to run in comparison to the mean and median filter, just as a result of the added algorithm complexity and elevation updating procedure. But this tool is still overall efficient, as parts of the algorithm have been optimized for parallel computing to take advantage of multi-core processing. So as of now, the tool has actually calculated the normal vectors, and it actually now is just working on the next procedure, and then it still has to go through the iterations updating parameter. So this tool does take a bit longer depending on your machine and the parameters you're using, but the output is extremely worth it in comparison to other filtering techniques. So we're just going to go ahead and wait it out. So now the tool smooth normal vector, that was the longest part of the algorithm. It took 54 seconds, and now it's just updating the iteration, updating the elevation, and now it's saving the data, and we are completed in 1 minute and 5 seconds. So thanks for hanging on as this process went through, and now we will continue with the video. So now that that's complete, once again, we're just going to create another hillshade for it as well. We're just going to set everything to the same thing, and we're just going to call this hillshade. Keep the parameters default, and we're going to run it. So now that the hillshade and the mean filter and the filters are all created, we can actually compare them in QGIS. So let's head over to QGIS to compare the differences. So we're just going to remove the actual DEM, as it doesn't really tell us too much here. So this is the unfiltered DEM hillshade. We're just going to go ahead and add the 3 other hillshades. So the feature preserving smoothing, the mean, and the median filter. I'm just going to go ahead and turn these layers off just so we don't ruin the big reveal. And I'm just going to put them in order of what I want to show them. Okay, and next I'm just actually going to make the min and max ranges the same, so it is a similar comparison. A lot of times when you're comparing DEMs or Hillshade, you're going to want to make sure they are the same min and max range, so you are getting a apples to apples comparison. So just bear with me through that process. It is a bit tedious, but it creates a more equal comparison when you're comparing multiple techniques. So now that that is done, all the DEMs, all the Hillshades are of the same min and max range, so we have an apples to apples type comparison. So as you can see, this is once again the unfiltered Hillshade. You can see it is quite rough in certain regions of the Hillshade. This flat area does have a lot of these lumps and bumps. The drainage features are pretty well incised, depending on where they're located. This is definitely more incised than other ones, but nonetheless, they're all important and they all need to be preserved as a result of smoothing. So let's check in on the mean filter, see what that DEM looks like. So as you can see, the tool did really well to remove all of the surface roughness and noise, which is great. That's kind of what we want a filtering technique to do. But however, you can see when you take a look at comparing the actual topographic features that they've been completely over smoothed and they are not what they were. Taking a look back at the unfiltered Hillshade, you can see the topographic expression here is much more representative of the true feature as opposed to this mean representation. You can imagine that running a flow accumulation on this DEM now will be a much different representation of its true form. So I would say that that has not done a good job to preserve the feature. Although a lot of the roughness, noise, and air has been removed, it's come at the cost of the topographic expression of these important features. So that's not great. Taking a look at the median filter, once again, this tool did pretty well to remove roughness and noise in comparison to the unfiltered Hillshade. But however, once again, looking at these important drainage features that exist in this DEM, they've been completely over smoothed and are actually not anywhere near close to what they actually look like. So that's not desirable. Once again, think about that flow accumulation algorithm that you have to run now. It's not going to be accurate in comparison to the unfiltered. So let's go ahead and look at the feature preserving smoothing technique. So this tool did well to remove a lot of the roughness, error, and noise. It did keep a little bit of it in the mountainous range, but that's kind of expected as it's such a dense forest cover. A little bit is going to be kept around. And once again, you could remove that further by playing around with the parameters more, maybe adjusting the filter size or adjusting the iterations to get more smoothing. So that could be kind of on the parameters I chose as a result. But let's take a look at these features, which is extremely important. As you can see, the features as a result of smoothing remain intact. Looking at the unfiltered Hillshade, you can see that these features are untouched almost, and their topographic expression has remained intact as a result of smoothing. This is more what you want out of a smoothing technique when you have these important terrain features that need to propagate further down into your analysis when running a flow accumulation algorithm. So this is kind of an approach you want to take. You want to choose a technique that works for your application. So it's about choosing intelligent techniques to conduct spatial filtering. So that concludes this video. I hope it has helped to learn how to effectively smooth your DEM using various smoothing techniques. Although the FPS smoothing technique was the superior method in this tutorial, in my opinion, it is better to treat each DEM application on a case-by-case basis. It may be that the mean filter may be more appropriate for your certain application, or maybe another type of smoothing technique, such as the Gaussian filter or bilateral. This tutorial was just to show you what types of smoothing option techniques are available to you in WhiteboxTools, and to show you how the choice of smoothing technique could impact your DEM as a result of smoothing. If you have any questions, feel free to ask them down below in the comment sections, or you can check out our Google group, or lastly, send us an email at support@whiteboxgeo.com. Please subscribe to our YouTube channel for all videos and updates. Thank you for watching.